Today, we are going to study principal component analysis, usually called PCA. PCA is one of the most important techniques in data science, machine learning, artificial intelligence, and statistics. The main idea of PCA is dimensionality reduction. That means we want to reduce the number of variables in a data set, but still keep the most important information. In real world data, we often have many features. For example, an image may have hundreds or thousands of pixels. A biomechanics dataset may have many joint angles, velocities, accelerations, and sensor signals. A medical dataset may contain many measurements from each patient. The problem is that high dimensional data is difficult to visualize, difficult to process, and sometimes difficult for machine learning models to handle efficiently. PCA gives us a mathematical way to find the most important directions in the data. These directions are called principal components. The first principal component captures the largest variation in the data. The second principal component captures the next largest variation, but in a direction independent from the first one. So, in simple words, PCA finds the best new coordinate system for the data where the most meaningful information appears first. This slide introduces the problem that PCA tries to solve. On the left side, we see the idea of a very high dimensional space. For example, an image with 640 by 480 pixels has many dimensions. If each pixel becomes one feature, then the data becomes very large and very difficult to analyze. This is called the curse of dimensionality. As the number of dimensions increases, the space becomes extremely sparse. Points become far away from each other. Visualization becomes almost impossible. Computation also becomes more expensive. But PCA gives us hope because many real datasets contain redundancy. Redundancy means that many features are related to each other. For example, in an image, nearby pixels are usually similar. In human motion data, the movement of the hip, knee, and ankle may be strongly related. In financial data, some market variables may move together. On the right side of the slide, we can see that the data points are spread mainly along one direction. Although the data may have many variables, the important structure may lie on a smaller number of dimensions. The goal of PCA is to find a compact representation of the data without losing too much information. This idea is connected to the Calhoun and Lobe transform, which is a mathematical foundation for representing data efficiently. This slide explains PCA using the idea of an encoder and decoder. Imagine we have original data in a high dimensional space. We want to compress this data into a smaller representation. This smaller representation is called a compressed code. The encoder maps the original data into a lower dimensional space. The decoder maps the compressed code back into the original space. In the slide, the original data is shown on the left. It goes through an encoder and becomes a compressed code. Then it goes through a decoder and becomes reconstructed data. In PCA, we assume that this compression and reconstruction process is linear. That means the relationship is based on straight line transformations, not complex nonlinear transformations. The formula on this slide can be spoken like this. The compressed code Z is obtained by multiplying D transpose with X. Then the reconstructed data X hat is obtained by multiplying B with Z. Here B works like a decoder and D transpose works like an encoder. The main question is this: how can we find the best projection matrix B? PCA answers this question using three different viewpoints. First, the maximum variance perspective. Second, the projection or reconstruction or perspective. Third, the probabilistic perspective. Now we begin with the first viewpoint, the maximum variance perspective. The main idea is simple. Information in data is related to how widely the data is spread. If the data varies a lot in one direction, that direction contains important information. If the data changes very little in another direction, that direction may contain less useful information. In the diagram, we see a cloud of points. The points are stretched mainly along one diagonal direction. PCA tries to find this direction. This direction is called the first principal axis or the first principal component. The mathematical objective is to find a basis vector that maximizes the variance of the projected data. The formula on the slide should be read like this: V1 equals B1 transpose multiplied by S multiplied by B1. Here B1 is the first basis vector. S is the covariance matrix of the data. V1 is the variance captured along that direction. But we also need a constraint. We do not want the vector to become infinitely long. So we require that the length of B1 is equal to 1. The constraint can be read like this: The squared norm of B1 equals 1. In simple language, we are asking this question. Among all unit length directions, which direction captures the largest spread of the data? That best direction becomes the first principal component. This slide shows how the maximum variance problem leads to eigenvectors and eigenvalues. To solve the optimization problem, we use a method called Lagrangian optimization. The Lagrangian combines the variance objective and the unit length constraint into one expression. The formula at the top can be read like this. The Lagrangian of B1 and lambda 1 equals B1 transpose multiplied by S multiplied by B1 plus lambda 1 multiplied by 1 minus B1 transpose multiplied by B1. Here lambda 1 is called a Lagrange multiplier. When we take the derivative and set it equal to 0, we obtain the fundamental eigenvector equation. The equation in the center can be spoken like this: S multiplied by B1 equals lambda 1 multiplied by B1. This is the key equation of PCA. Here S is the covariance matrix. B1 is the eigenvector. Lambda 1 is the eigenvalue. The eigenvector gives the direction of the principal component. The eigenvalue tells us how much variance is captured in that direction. So the conclusion is very important. The optimal subspace is spanned by the eigenvectors associated with the largest eigenvalues of the covariance matrix. In simple words, PCA keeps the directions with large eigenvalues because those directions contain the most information. This slide shows why PCA is practically useful. Here, the example is based on handwritten digit images, especially the digit 8. Each image has 784 dimensions. This happens because a 28 by 28 pixel image has 784 pixels. If we use all 784 dimensions, the image can be represented fully, but PCA shows that we may not need all of them. On the graph, the horizontal axis represents the number of principal components. The vertical axis represents captured variance. At the beginning, the curve rises very quickly. This means that the first few principal components capture a large amount of important information. After some point, the curve becomes flatter. This means that additional components add only small amounts of new information. This is called eigenvalue drop-off. The eigenvalues decrease rapidly, meaning the later components contain less meaningful structure. For example, if we use too few components, such as one component, the image becomes a generic blur. But if we use many more components, such as 500, the reconstruction becomes almost visually lossless. The key message is this: PCA helps us decide how many dimensions are enough. Now we move to the second viewpoint, the projection perspective. Instead of asking which direction captures maximum variance, we ask a different question. How can we reconstruct the original data with minimum error? In the diagram, the original point is shown away from the orange line. The orange line represents the low dimensional subspace. The projection of the point onto the line gives a reconstructed point. The difference between the original point and the projected point is the reconstruction error. The objective function on the slide can be read like this: J sub m equals 1 over n multiplied by the summation over n of the squared norm of xn minus x hat n. In words, this means the average reconstruction error is calculated by measuring the squared distance between each original data point and its reconstructed version, and then averaging over all data points. The geometry is based on orthogonal projection. Orthogonal means perpendicular. So, the shortest distance from a point to the subspace is the perpendicular distance. PCA chooses the subspace that makes these perpendicular distances as small as possible. This viewpoint is very intuitive. PCA is not only maximizing information, it is also minimizing what we lose during compression. This slide continues the projection idea. When a data point is projected onto a lower dimensional subspace, the error vector points in the direction that is perpendicular to the subspace. This perpendicular region is called the orthogonal complement. The first insight on the slide is that the displacement vector lies strictly in the orthogonal complement of the principal subspace. In simple words, the error is exactly the part of the data that PCA throws away. On the right side, we see the low rank approximation idea. The formula can be read like this: X is approximately equal to B multiplied by B transpose multiplied by X. Here, X is the original data matrix. B contains the selected basis vectors or principal components. B transpose maps the data into the lower dimensional space, and B maps it back to the original space. This is why PCA is also connected to matrix approximation. The second insight is that finding the optimal basis vectors is equivalent to finding the best rank M approximation. Rank M means we use only M important directions instead of all original dimensions. So PCA gives us the best possible linear low dimensional approximation of the data. This slide connects the two previous viewpoints. We have already seen two ideas. First, PCA maximizes variance. Second, PCA minimizes reconstruction error. At first, these may seem like different goals, but mathematically they are equivalent. The diagram shows a right triangle. The original data vector has a fixed length. One part is the projected vector. The other part is the reconstruction error. Using the Pythagorean theorem, the squared length of the original vector equals the squared length of the projected vector plus the squared length of the error vector. The formula can be spoken like this. The squared norm of x equals the squared norm of x hat plus the squared norm of x minus x hat. The important idea is this. If the original data length is fixed, then minimizing the reconstruction error is the same as maximizing the length of the projection. That means minimizing error and maximizing variance are two sides of the same coin. The result at the bottom says that the reconstruction error equals the sum of the discarded eigenvalues. This can be read like this. J sub m equals the summation from j equals m plus 1 to d of lambda j. In words, the total error after keeping m components is equal to the sum of the eigenvalues that we did not keep. This slide explains two practical ways to compute PCA. The first approach is eigendecomposition. In this method, we first compute the covariance matrix of the data. The formula can be read like this: S equals 1 over n multiplied by x transpose. Then we solve the eigenvalue equation. S multiplied by b equals lambda multiplied by b. This gives us the eigenvectors directly. These eigenvectors become the principal components. However, this method requires computing the full d by d covariance matrix. If the number of features is very large, this can be expensive. The second approach is singular value decomposition, or SVD. The SVD formula can be read like this: x equals u multiplied by capital sigma multiplied by v transpose. Here x is the original data matrix. E contains directions related to the eigenvectors of the covariance matrix. Sigma contains singular values. V contains another set of orthogonal directions. The slide also says that the squared singular values relate to the eigenvalues. This relationship can be spoken like this: lambda d equals sigma d squared divided by n. SVD is often more numerically stable than directly computing the covariance matrix. It also uses the Eckart-Young theorem, which tells us that the best low-rank approximation is obtained from the largest singular values. So in practice, many PCA implementations use SVD. This slide explains an important computational trick. Suppose we have 10,000 pixel images. Computing a 10,000 by 10,000 covariance matrix is very expensive. It may be computationally unstable and difficult to store in memory, but sometimes the number of samples is much smaller than the number of dimensions. For example, we may have only 500 images, but each image has 10,000 features. In this case, instead of computing the huge D by D covariance matrix, we compute a smaller n by n gram matrix. The smaller matrix can be spoken like this: x transpose multiplied by x. This matrix is only 500 by 500 in the example, which is much easier to handle. After we find the eigenvectors of the smaller matrix, we multiply them by the centered data matrix to recover the true eigenvectors of the original high-dimensional covariance matrix. The recovery idea can be spoken like this: multiply the resulting eigenvectors by x centered. This trick makes PCA practical for high-dimensional datasets, especially image data, sensor data, and biological data. The main lesson is that PCA is not only mathematically elegant, it is also computationally efficient when implemented carefully. This slide summarizes the practical PCL algorithm step by step. Step 1 is mean subtraction. For each feature, we subtract the mean value. The formula can be read like this: x minus mu. In words, we take each data point and subtract the mean. This centers the data around the origin. This step is important because PCA depends on variance around the mean. If we do not center the data, the first principal component may be influenced by the location of the data rather than the direction of variation. Step 2 is standardization. If different features have different units or scales, we divide by the standard deviation. This can be spoken like this: divide by sigma d. For example, if one feature is measured in meters and another in millimeters, Their scales are very different. Standardization prevents one large scale feature from dominating the PCA result. Step 3 is eigen decomposition. We solve the eigenvalue equation. S multiplied by B equals lambda multiplied by B. This gives us eigenvectors and eigenvalues from the covariance matrix. The eigenvectors show the directions of the principal components. The eigenvalues show how much variance each component captures. Step 4 is projection. The projected version of x can be spoken like this: x tilde equals b multiplied by b transpose multiplied by x. Inwards, we map the data onto the principal subspace defined by the top m eigenvectors. So the PCA workflow is: first, center the data; second, standardize if necessary; third, compute the principal components; fourth, project the data into the lower dimensional space. This is the basic practical pipeline used in real data analysis. Now we move to the third viewpoint, the probabilistic perspective, also called probabilistic PCA or PPCA. Standard PCA is deterministic. It assumes that data is mapped exactly using a linear transformation, but real world data often contains noise. The first formula can be read like this: x equals bz plus mu. This means that the observed data x is generated from a latent variable z transformed by b and shifted by the mean mu. But this model does not explicitly account for noise. Probabilistic PCA adds a noise term. The second formula can be read like this: x equals bz plus mu plus epsilon. Here, epsilon represents Gaussian observation noise. This changes PCA into a generative latent variable model. The assumptions are: the latent variable z follows a standard normal distribution. This can be spoken like this: z is normally distributed with mean 0 and identity covariance. The observation noise epsilon is also Gaussian. This can be spoken like this: epsilon is normally distributed with mean 0 and variance sigma squared times the identity matrix. Why does this matter? Probabilistic PCA allows us to handle missing data, calculate model likelihoods, and generate new synthetic data points. So PCA gives PCA a statistical foundation. It connects dimensionality reduction with probability theory. This slide shows how probabilistic PCA can generate new data. Instead of compressing existing data, PCA can work in reverse. The process starts in the latent space. First, we sample a latent vector from a normal distribution. This can be spoken like this: sample Zn from the normal prior. Then we push this vector through the learned parameters. The next step is multiply b by Zn. Then we add the mean, add mu. After that, we add Gaussian observation noise, add epsilon. Finally, we obtain a new output data point. The full generative expression can be spoken like this: x equals bz plus mu plus epsilon. This means PCA can simulate new data points that follow the same structure as the original data set. For example, if the model is trained on handwritten digit images, it can generate new digit-like images. If it is trained on motion data, it can generate new motion-like patterns. This is why the slide calls PCA a generative model in the probabilistic setting. The key idea is that PPCA does not only reduce dimensions, it also explains how data may have been generated from hidden latent variables. This final slide brings everything together. We studied PCA from three perspectives. The first perspective is maximum variance. The objective is to retain maximum signal or maximum spread in the data. The mathematical idea can be spoken like this: maximize B transpose multiplied by A multiplied by B. Geometrically, this means finding the widest access in the data cloud. The second perspective is projection. The objective is to minimize reconstruction error. The mathematical idea can be spoken like this: minimize the square norm of x minus x hat. Geometrically, this means dropping perpendiculars from the data points to the principal subspace and making those distances as small as possible. The third perspective is probabilistic PCA. The objective is to maximize the data likelihood given latent variables. The mathematical model can be spoken like this: x equals bz plus mu plus epsilon. Geometrically and statistically, this means generating data from a low-dimensional latent space with noise. These three viewpoints seem different. One comes from signal processing, one comes from geometric optimization, one comes from probability theory, but all three lead to the same mathematical result. The important directions are the eigenvectors of the covariance matrix. This is the universal truth of PCA. So, the final takeaway is: principal component analysis is not just a technique for reducing dimensions, it is a powerful framework for understanding structure in data. It finds the directions where information is strongest, removes redundancy, reduces noise, improves visualization, and supports efficient machine learning. That is why PCA remains one of the foundational methods in data science, artificial intelligence, image processing, biomechanics, and many other scientific fields.